I think the main misconception is that it's easy, right? And people often come to CFD from other problems or other courses where it's easy to know the errors, it's easy to find the bugs. And CFD, it's complex. It's a complex topic, so you have to run simulations sometimes for long times to then find the error.
Welcome to a new episode of the Engineering Mind podcast. I'm your host Yusuf, and on this podcast I'm talking to researchers, scientists and engineers and how their work is shaping the world around us. For this episode, I'm very excited to talk to Esteban Ferrer on my show. Since 2021, Esteban holds a professorship in applied mathematics at the School of Aeronautics in the Universidad Politécnica de Madrid, which is one of the top schools of aeronautics in Europe with a high reputation in fluid mechanics. Esteban is coming from an unusual academic trajectory since he completed his PhD in 2012 at the University of Oxford, but had 6 years of previous work experience in industry. Altogether, he has more than 20 years of academic industrial experience in numerical techniques for fluid problems and wind turbine design for energy generation. In this podcast, Esteban and I discuss Horses 3D, a high-order discontinuous Galerkin solver for flow simulations and multiphysics applications. We talk about academia versus the industry and what made Esteban go back to academia. We also talk about prerequisites to write your own CFD solver. We'll talk about the finite element method, the finite difference method, as well as the finite volume method and the drawbacks of some of those. Esteban covers misconceptions about CFD and CFD solver development and so much more. If you would like to support the channel, make sure you give this video a like and leave your comments down below. Subscribe if you haven't already. And now, ladies and gentlemen, here's my podcast with Esteban Ferrer. Esteban, welcome to my show.
Hello, Seth. Thank you for having me.
Thanks for doing this very interesting podcast as well. Last week we had Ricardo on the show talking about CFD and machine learning. This week we have another expert on the show who will talk about CFD and machine learning. But before we jump into CFD and CFD solvers and how you get started actually writing a CFD solver, can you give the audience a little bit of a background? Who's Esteban? What do you work on? What is your profession?
Sure. So I'm a professor in applied mathematics in the School of Aeronautics in Madrid. And I had a little bit of a different background of the usual, let's say. So when I finished my degrees, I went to industry for a while. I worked in industry for 6 years, which is quite long in typical standards in academia. But then I wasn't very pleased with industry in the sense that I wanted to get deep into CFD in particular. And then I decided to go to Oxford to do a PhD. And that's how I started. Well, how I went back to academia. And then after the PhD, I got a postdoc position in Madrid, and then a lectureship, and then a professorship. So a little bit of a different background, which I think it's kind of interesting because it gives you another perspective of academia as well, no? How academia can interact with industry, how you can do things a bit slightly differently. So just a quick recommendation. So if I would recommend people to go to industry after they finish their degree and before they start a PhD. I think that's very interesting. It gives you another point of view. However, I wouldn't wait 6 years, which is what I did. I think 6 years, you end up having to catch up for a lot of things in terms of publications and things like that. And it's a bit stressful after if you wait a lot of time. So I would recommend maybe a couple of years or something like that. I think that's pretty good.
Mm-hmm. Can you maybe give the audience a bit of a pros and cons, academia versus working in the industry? What is your personal opinion on that?
Okay. So at least, that's very difficult to generalize. So, I can talk about my perspective and the industries where I was.
Mm-hmm.
And I think it was very interesting to be in industry for a while. The downside of industry that I don't really like so much is that things has to be done very quickly, right? So you have maybe 3 months to finish a project, maybe six months maximum. You don't have enough time to go very deep into things. And typically in academia, you do have time. So you have PhDs, which are longer, 3 years, something like that. And that allows you to explore much more in depth, interesting concepts. And in that sense, I really prefer academia. It's true that academia can be a little bit abstract sometimes, right? So I think for the abstract in the sense that you don't apply really what you are doing to a final aim, right? You don't see the what you're building, right? That you do see in industry. So in that sense, I think it's interesting that academics work within industry and try to get the best of both worlds. So we tend to do that. We tend to work a lot with industry, and I think that's an interesting synergies. There's interesting synergies there.
Interesting. What made you decide to go back to academia?
Right. I was working with CFD and mainly commercial codes, and it seemed to me a bit frustrating that sometimes things didn't work. Right. So if things didn't work, you will change the mesh, you will change the grid spacing, you will change you will go from first to second order, you could change, the things that you are allowed to change in a commercial code. And that wasn't very, I don't know, I didn't like that approach very much, because it's a very confined framework that you can, a very few set of parameters you can play with. So I wanted to really be able to change the code if it wasn't working, right? So get into the code and change things. And for this, I thought doing a PhD in CFD and building my own CFD code, that was the best option, right? You control absolutely everything that's going on, and you can change things if things don't work, right? So and you know how to change it. So that gives you a complete control or complete understanding of everything that is going on. So this was mainly my motivation, I think.
That's a pretty cool motivation. I think what interests a lot of people, Esteban, is can you give us, like, from your own experience, like what prerequisites or what knowledge did you need to have in order to actually get started with your own coding? Was it like programming skills that you were lacking, or how did you approach such a project in the first place?
Well, I think first you need a good background in mathematics, I think, and fluid dynamics. And there's a lot of resources now online. I'm a little bit of a classic person, so I would recommend people to join a master degree or something like that to get the specifics of CFD. The problem that I see in the resources that are out there is that they all focus in finite differences or finite elements or finite volumes, right? And it's difficult to know when you're learning which method is the best for your application or how you approach each of the different methodologies or schemes, etc. I think it's overwhelming. You have too many different time advancing schemes, too many spatial schemes, and what do you do, right? So I think if you go to a nice course, to a nice master, or you have a nice professor or tutor or whatever that can guide you a little bit in all this ocean of methods, that can really help, right? Not to get completely lost. Again, there is online courses as well. I think that those are very useful. I would say to complement the classic approaches, the classic courses. I myself, my aim is to add some videos. I have recorded some videos as well for CFD, for learning CFD, and the aim is to start uploading them online to my website as well in the near future when I have time.
Sounds good. And I will share them then after the podcast. Once the podcast is live, I can share them, and once you uploaded them, I'm happy to share them with the community. What are your videos mainly focusing on? Like, what is the main focus of those videos?
Of what, sorry?
Of the videos that you will be uploading.
I think what's actually missing out there, which is kind of comparing the different methods. So giving an overview of finite differences for fluids, finite elements for fluids, finite volume for fluids. I mean, all these different methods, they're all very, very good. I mean, they're all obviously good, but they have some differences, right? And the mathematical background of each of them is quite different, although sometimes the method in the end, algebraically, is exactly the same. But, the way you approach them is completely different. I think it's interesting to know the different ways how to construct numerical methods.
Yeah. Can you give us... Sorry, Esteban. Can you give us maybe concrete examples? Because you mentioned FBM, FEM, and FVM. Can you give us concrete examples where you would use these methods and where you wouldn't use these methods?
Right. So Well, what we do, I'll tell you what we do, which we think it's the best approach, is we use higher order methods, right? And in higher order methods, in particular Discontinuous Galerkin, you can have a bunch of different methods within the one unique method, right? So basically, when you change the polynomial order, so the way it works is you have your mesh, typical mesh, which we call H mesh typically. And then inside each element, we have a polynomial order, which can be of arbitrary degree. And what we can do is increase the polynomial order to get a better solution inside each of the elements. When we do this, what we get is exponential convergence of the error. That means that the error decays very, very quickly, and we get a very accurate solution when we increase the polynomial. But so that's very nice property, and we use that a lot when we run cases with high polynomials. However, what's interesting as well is that if you downgrade to a polynomial order 0, you recover a finite volume method. So basically, you're running a finite volume method. If you run with P1, you're running something that is very similar to that of finite elements, where the solution changes linearly inside each element. And you can go beyond that and run P2, P3, different polynomial orders, high polynomials. We typically run P5, for example. So what we like about these methods is that they give us the opportunity of running different discretization schemes only with one particular framework. And that's quite useful, right? You don't have to rewrite the code every time. You just change polynomial order equals 0, 1, or whatever, and in runtime, and that's fine. This versatility gives us the opportunity to run complicated cases where one method is better than the other. For example, if you have a shock wave, higher order methods are not very, very good because basically you have Gibbs phenomena. So oscillations, if you use a very high polynomial order inside the element and the shock is in the element, right? You will have oscillations. Then you typically you either add viscosity in the element or you can downgrade the polynomial to a low order method, right? And low order methods are good at capturing the shocks. Of course, you can combine that with mesh adaptation and other things. But so in that sense, this higher order setting, the higher order discontinuous Galerkin allows you to locally downgrade the polynomial to 0 new shocks, but have a high polynomial order away from the shocks, for example, boundary layers, etc. So that's a nice framework in the sense that combining higher order methods with mesh adaptation, you can do a lot of things for complex problems. And this is a little bit our motivation of using these higher order methods.
What would you say are the drawbacks of these methods that you're using?
Well, the drawbacks are they're not mature enough yet. So in terms of people have the concept that higher order methods are not very robust, and that was true before Discontinuous Galerkin and these very new methods had come along. So it was true that with continuous higher order methods, they weren't very robust. There wasn't enough numerical viscosity, local numerical viscosity in the elements to stabilize the solution. So those were prone to crash or to blow up. Now, with the new methods, so this includes Discontinuous Galerkin or flux reconstruction methods, those have you have discontinuities in the solution between elements, right? So you allow for discontinuities, hence the Discontinuous Galerkin name. And you have a Riemann solver that links the solution between the elements. This Riemann solver, or these fluxes, allows you to add a little bit of dissipation in between the elements, not inside, but in between the elements. So this very little dissipation that you add tends to stabilize the solution. And this stabilization allows you to run high Reynolds numbers, and it makes the solvers much more robust as they were before when using continuous Galerkin or higher order spectral methods, let's say. So in the old times, the higher order methods were only used for very low Reynolds numbers, right? For very accurate low Reynolds number solutions, instability analysis, this kind of analysis. Now, with this new family of methods that have a little bit of dissipation, you can run more interesting cases, more complex cases, and actually industry is interested in using these cases as well. So we are actually working with industry because they see a potential in using these methods for complex applications.
Yeah. Could you name a few examples? I mean, you talked about, for example, resolving shock, like shock waves, for example. Could you talk about industry examples where this would be a promising solution, like a few cases?
Yeah, we've run, for example, runs for complete aircraft, runs application for aircraft, and those benefit from higher order methods because, of course, if you use runs, you have a smooth solution. Higher order methods are very good at capturing smooth solutions, and what you see is that with fewer degrees of freedom, you attain the same accuracy as with a low order method. So increasing the polynomial allows you to decrease the error much faster. And because you do that, you can use fewer degrees of freedom that you will use in a lower order setting. So basically, fewer degrees of freedom means that you can solve the problem faster, right? So you need less memory in your computer to solve it. So there is this benefit, and there's a potential of using these methods for very large computations. Of course, there's other issues. I mean, there's some drawbacks still, which is that the numerical part of solving the equations and inverting the matrices or solving the linear systems, it's not completely mature in the sense when applied to higher order methods. So this is something that we are working in. So preconditioning the matrices arising from higher order methods, multi-grid for higher order methods, all this kind of stuff. It's very well defined for lower order methods, but not so much for higher order methods. So these are things that still to be a little bit mature. But once those are ready, and they're ready for a few cases, then higher order methods should be better. They have to be better than lower order methods in the sense that fewer degrees of freedom with higher accuracy.
Got it. That makes sense. I was wondering, though, the question might come up for a beginner in CFD. Why wouldn't we go even for higher polynomials, let's say 7, 8, or 9th degree? Why not? Can we?
Yes. I've run cases with polynomial order 20. There's no problem. But all these things that we're talking about, so preconditioning the systems, solving the systems, those become harder and harder, or not harder and harder, but they become more and more different from lower for everything we know from lower, right? So if you are polynomial order 2, 3, you are close to P0, which is the polynomial 0, which is the finite volume. There's a lot of literature and libraries available out there to solve this. But if you go to P20, the matrices are completely different. So, you have to develop much more stuff. I think that's the main issue.
I see.
And also, I guess in Discontinuous Galerkin, this small diffusion that you add in the elements, between the elements, you lose it if you use a very high polynomial. You will use a very, very big element with a polynomial of the 20, right? And then you will lose the small dissipation that helps you stabilize. You don't lose it, but you have fewer interfaces, right? So you have you're recovering Fourier methods kind of thing, right? And with Fourier method kind of things, you end up having the old troubles of stability, perhaps.
I see.
So there is a trade-off. You want to go with high polynomial orders, but allowing this small dissipation to help you to stabilize the simulation in case there's a small instability arising.
I see, that makes sense. I was wondering, you talked about discontinuous Galerkin. You explained the first part, discontinuity, and then the second part would be Galerkin. Why Galerkin and not any other method? What's very promising about that one?
Well, what we like about this continuous Galerkin is that all fits in the framework of finite elements. So it's a variational form, right? It can be thought as you're looking for the best solution in the space of polynomials, right? That define the space where you're looking for the solutions. So these ideas are nice because then you can do analysis, you can find errors. So there's a lot of literature on how to find errors with finite elements, right? And do error analysis for this. So this is, in that sense, beneficial. I will say that we have also used other higher order methods. So flux reconstruction, we also use flux reconstruction, which doesn't have these settings. So we like discontinuous Galerkin, but we are not completely blind by discontinuous Galerkin. We use also other methods.
Got it. I was wondering, maybe you can delve a little bit deeper into FEM for CFD, because we never had that on the podcast, and I think it would be interesting for people listening to this show is why would you use FEM or like the principles of FEM for a CFD problem? What's promising about that?
Well, I think it's the main advantage is what I mentioned. It's all the error and mathematical machinery for error analysis that it's behind the thing. So, in a sense, finite elements are nice because they tell you that you're looking for the best possible solution, right? So if you use polynomials, you are solving that variational form. It's telling you that you're getting the best solution possible within the space that you have defined, this finite space of polynomials. And this is a nice thing that it's not at all obvious in other methods. In finite volume, you are getting a solution, but is that the best solution you could get? Not necessarily, unless you go to the finite element framework and you recover finite volume from that framework, right? But I think it's about the mathematical machinery that it's nice. It gives you some security on the framework you're using and the mathematics behind.
Got it. Okay, that makes sense. I was wondering though, Esteban, maybe you could walk us through, because you developed your own code. I'm not sure if that's a wordplay. Is it Horst 3D or is it Horst Dead when you pronounce the name of the code that you've developed?
I would call it Horses 3D.
Horses 3D. Okay, I was thinking it's a wordplay or something.
Yeah.
Anyway, maybe when you started developing the code, maybe from the beginnings, how did you actually get started? Because you were frustrated about commercial codes. Did you have a plan in mind? How did you actually get started? Deriving all the equations, and how did you actually start implementing those? I think that would be very interesting.
Right. So I should mention that the code that I wrote during my PhD is not Horses 3D. It's a different code.
Got it. Okay.
And the point about this is, I think, so when you develop a code, it's your child, right? So you love it and you spend a lot of hours with it, and well, it's difficult to let it go sometimes, right? So you want to keep working on it, etc. But I think it's important to let it go sometimes, right? When there's another code that has more potential and you start working in another code, or when you see that some of the features are not enough for what you're doing, etc. So it's a difficult thing, but it's an important thing to do sometimes, right? So that's what happened to me. So I developed this code during my PhD, which was also higher the discontinuous Galerkin, with light meshes in particular. But then in the department, we were starting to develop this other different code, Horses 3D. And at some point I had to decide, right? So let's put the efforts in Horses 3D, because otherwise you cannot maintain two codes and keep developing the code. That's too much. And we put all our efforts in Horses 3D, and that's what we're doing now. How did we start it? I think starting a code is probably the most difficult part, right? And I think what's very important is to know the aim of the code. So what do you want the code for? So if you want the code to have very fast computations in HPC facilities, right? For DNS, for example, for DNS or turbulence or whatever, that's a very different approach than having a general code that can solve a variety of problems as the one we have, right? So all the versatility that comes with different polynomial orders, different type of discretization schemes or temporal schemes, being able to solve different problems. For example, we have multi-phase things. We can do aeroacoustics. We can do a variety of incompressible and compressible flows, etc. So this versatility comes at the cost of maybe not being as efficient as if you are only solving one polynomial order for incompressible flows and just for a channel, right, to get the turbulence right. So one needs to know the aim. So what do you want your code for from the beginning, right? And based on that, you think of the architecture of the data. So am I going object oriented, or am I having just a fixed, array of solution how I can order the data to have the most efficient HPC thing. But that's a very important thing, and I don't think people think enough about that, right? So we work with students. We get students to develop new features in the code, right, and use different applications, and sometimes you have to change a little bit the code to do that. So for us, having a code that is very that can be changed and hence going to an object-oriented structure of the data, where you have a lot of flexibility, right? Adding new attributes to the variables, things like that. Everybody can do that. That that's very good for us. That's very good for us, and we can run a lot of these things. Now, is our solver as efficient as a solver that only runs one polynomial order for turbulence? I'm sure it's not. I'm sure it's not. Okay, because we have the versatility, and we have to pay a price, which is it's very difficult to optimize for all polynomials, for all all features, etc. So this to me is the most important thing. What do you want to do with your code? If it's only for learning, go to something that it's easy to change, right? If you're going for production, let's fix all the parameters that you can and start from there.
Interesting.
Well,
That makes a lot of sense. Yes. You were talking about your students. Like, I would like to know from you, when students are getting started with CFD, what would be their biggest misconceptions, maybe in terms of developing CFD code? What are they mainly struggling with, if they are struggling, not assuming that they always struggle?
Well, we all struggle with CFD,
That's true.
so not only students. I think the main misconception is that it's easy, right? And people often come to CFD from other problems or other courses where it's easy to know the errors, it's easy to find the bugs. And CFD, it's complex. It's a complex topic, so you have to run simulations sometimes for long times to then find the error, right? And that's very frustrating. That's if you're running turbulent, for example, turbulent cases, you might need to wait for a long time until you get some instability that it's messing up all your solution, and then you have wasted maybe I'm going to be optimistic, maybe 6 hours of computing time until you find the problem. And that's very frustrating because you have lost 6 hours or maybe 1 day of computing time until and you find the error, and then you try again. So it's very important in CFD, I think, to simplify the problem as much as you can, to maybe, if you're looking at turbulence, a very small box with turbulent flow inside, right? So Taylor-Green vortex comes to mind, which is a classic problem to test turbulent things. And this can run fast. So don't go for the aircraft, right? Don't run a turbulent. If you're testing your code, never run an aircraft. That's a typical error for students. No? Go to the final application, and that's very frustrating. So you want to start easy and go up in complexity.
I was wondering, when you started learning CFD, if you think back now, maybe give young Esteban advice on how to start CFD. What would you tell the young Esteban? How to get started? Maybe avoid unnecessary resources. What would you tell him?
I don't know. Be patient, I guess. That would be the first one. And I guess try to get advice as well. No, don't be stuck on your own, right? Trying a lot of things. I mean, of course, you have to, when you're debugging of these things, you have to be on your own and you have to debug that kind of alone. But it's also nice to try to collaborate with people, right? So I think at the very beginning I was quite alone developing my code. Of course, there was people in my lab also doing similar things, and then I could chat to people. That's very important. If you don't chat to people, then you just die. But also try to collaborate. Maybe I think that's nice.
Yeah.
So, for example, now our code is online, right? So it's at GitHub. So if people are interested in collaborating, we're happy to to talk and try to collaborate. If they want to add new features, we can maybe help them a little bit or whatever. So I think that's also, you don't always have to start from scratch, right? So you start from scratch when you are learning, right, to write a code. Perhaps I think that's important. You learn how to write a code, maybe a small code, but then at some point maybe you can jump into horse 3D, for example, and then collaborate with people that know a bit more than you, and then keep I think that's also important and interesting.
Good advice. I was wondering, Esteban, do you think that a lot of people in academia, not only maybe in the CFD community, think that everything is like a zero-sum game? So some people don't even want to collaborate or share their code open source. Do you think that's a problem? Or do you see it like that? Or do you feel that the CFD community is itself very helpful? And
Well, I mean, to be honest, we haven't shared our solver for a long time, but not because we were scared of, I don't know, people stealing ideas and things like that. It wasn't about that. It was about we were scared of suddenly having a lot of people wanting to collaborate and we not being able to support these requests, let's say, no. So I think you need a nice documentation so people can try to work on their own and these kind of things, because of course we are only a few academics supporting this solver in particular, and then the rest are students that come and go, and it's very difficult for us to to answer all the questions. It's not compiling well. I don't know. I cannot sit with you and compile the code in your machine. That's I don't have time for that. Sorry. So we have spent some time in putting together the documentation, and we still have to add some tutorials and things like that for easy cases. So this is something we still have to do, which is necessary. And so this is why it took us a long time to make it available, because we were scared of not having time. We're not a super big group, so we didn't have time for that. Of course, if you go to OpenFOAM, these guys have particular departments, that do that. They give support. We don't have.
yeah,
But that being said, we have, for example, a discussion forum in GitHub, and the idea is to answer the questions that arise in the discussion forum, so everybody can see them. And we will connect every so often and answer some questions, and hopefully we can build a small community of people working on the code and sharing the knowledge. So that's.
I will definitely share the link of the GitHub repo in the comments. So if anyone wants to collaborate with Esteban and the community, feel free to do so. Esteban, I was wondering, and then we jump to another topic, is while you were developing the CFD code, maybe from your own perspective, and of course, everyone has their own journey, CFD journey. What were you struggling with the most? Of course, you gave us tips on what to focus on, like versatility versus focus on a specific problem. But what were you struggling with the most? Is it like starting the code, like where do I start, where do I get started? Or was it a specific problem that you were stuck with during development?
For me, when I was doing my PhD, for example, the most problematic part was turbulence. So getting the code running, running normal low Reynolds number flows. I'm not going to say it was easy, but it wasn't the most difficult part. Now, the part on turbulence and how to stabilize high order methods to get a nice turbulent, without adding a lot of diffusion to stabilize it, but getting nice results with turbulence, that was very difficult. And it was very difficult a little bit for what I already mentioned, right? That you have to wait a long time until things blow up. And sometimes I was waiting. Of course, my solver at the time wasn't that well performing, so I then spent some time profiling, etc., to get it to get accelerations. So I was waiting maybe for 4 days, and then it was blowing up, and I was finishing my PhD, and I was waiting for 4 days, and it was blowing up. And I remember telling to some friends of mine in Oxford that I was waiting for one dot in a lift angle of attack curve for a profile, a 3D profile with turbulence, and I was waiting for one dot to finish, and it will keep blowing, right? So I ended up getting it, but it was very frustrating. So I think these things, and I think maybe I didn't apply properly the advice that I just gave to the audience, right? That it's start with a smaller case, start with an easier case until you really understand what's going on with turbulence and dissipation and all these things, until you go to the final applications. I went crazy because I was finishing my PhD. I wanted to, be a bit faster in getting the results, and it's not faster if you go to the final application. So these days, what we do is we do a lot of analysis on the numerics, right? So every time we develop a new subgrid model or something like that, we do von Neumann analysis, which is one-dimensional analysis to get the dispersion and dissipation errors right of the numerics, right? We get that under control, and then we do a one-dimensional Burger's turbulence, for example, which gives you some idea of turbulence, but it's 1D, so it runs faster. And then we jump into Taylor-Green vortex, which is a 3D box, right? So not so many problems with boundary conditions. And then finally we go to channel flows and things like that to see the effect of walls. And then after that we will go to an aircraft or something like that. So some final application. But we try to understand really what is the behavior of the errors and what's the behavior of dissipation, dispersion, in all the different steps.
Yep.
So
There were,
I didn't do that during my PhD. That was an error.
Okay. But that was a quite good roadmap, Esteban, that you just gave the audience. So if they want to get started using or develop their own CFD code, I think that's very good tips. Maybe I'm assuming you got started maybe with developing in C++, and with the uprise of new languages, new quote unquote, such as Julia, do you see like there's a movement going away from C++ more to more modern languages?
I think so. I think Julia it has a lot of promise, right? So it looks very good. Of course, you're betting on something that is not well established. So, and there's always a risk on that, right? So you don't know if in 4 years there's another language that it's gonna, just eat Julia away. So it's nice. I will use it, and I have used it a little bit. I think it's interesting. Now, will I bet all my money on it? I'm not sure. That's a difficult question. I don't know what to say about that. I think C++, we use Fortran for horses, for example. I use C++ in other codes. Those are well established, right? So it's difficult that they completely disappear. So there's new standards coming up, there's new features being added. So I don't know. I mean, for us also there's other things that you have to consider when you develop a code. For example, in our school we teach Fortran in the first years. So the students that arrive to us to do a master degree or to do a final degree project or something, they know Fortran. So it wouldn't make a lot of sense to have a different language for our solvers, right? Because they already know this one.
Yep.
So there's also some politics, let's say, behind selecting the language. It's not all about efficiency. It's not all about how easy it is to code.
No, that's true.
But that being said, my advice is use a language that where you're comfortable, right? So, and then worry about the performance later. I think I've seen MATLAB codes that were very efficient. So and people tend to always say that MATLAB is not very efficient and stuff. So I think again, it's all about the aim, right? The aim can be develop a code, learning, right? You're learning the code, or you want to run huge simulations in HPC systems. Those are different codes, completely different codes, right? For the learning, you use the language that you're comfortable with, and then you worry about the maths, you worry about other things, right? And for efficiency, maybe you write it in one language, and afterwards you either profile this language or maybe you have to translate it to another language. That's not super difficult to do either. If you have one working thing. If you don't have anything working, that's very difficult to do. But if you have one working thing, making that working thing in another language or in the same language efficiently, it's not too difficult. You have the numbers to check if you've done it right.
Yeah.
So.
Absolutely. From your perspective, when did you first get in touch with machine learning used for CFD? Why did you maybe jump on the, let's call it, hype train? And what was the promising, why is it promising in the first place to use AI for CFD?
Okay. I think it wasn't too long ago, maybe 2 years ago, that we started looking at machine learning. And of course, it was because everybody was using it, right? So we thought, I'm not very keen on abandoning CFD, right, and using machine learning instead, these kind of things. There's some trends on that. What I really like is combining both, right? Combining CFD and maybe using machine learning for some particular tasks, or using machine learning to try to accelerate CFD, right? So, for example, things that we've been doing, we're using clustering, for example, for mesh adaptation. So we're trying to find the regions that have where we have to use a high polynomial order, right? And for this, we can use clustering, which is quite efficient. There's lots of tools to do clustering. You need the right variables to throw into the clustering thing, but I think we have some quite good ideas on how to do that. And we think that can be an alternative to classic adaptation methods that we have worked with as well in CFD. So that's one thing we're doing. Another thing we're doing, which we think it's very interesting, it's in higher order methods we have we can change the polynomial order inside each element, right? So what we can do is we can run a very high polynomial order, P8, for example, and get a very nice solution. And this we've done for turbulent flows, for three-dimensional turbulent flows. But of course, P8 is very costly. It's a solution that it takes a long time to converge for two reasons. You have a lot of degrees of freedom, and you need a small time step, right? The time step relates to the CFL condition, and you need a lower CFL if you have a fine discretization, which is the polynomial order 8. So this is a very good solution, but very costly. So what we can do is run a P3 solution, a much lower polynomial order, and then compute a correcting forcing that takes you from the P3 solution to the P8 solution. And this corrective forcing that you compute in each node in your mesh comes from machine learning. So the machine learning is the one that is going to get this corrective forcing, right? So you do some training for a little while, and then after that, you stop the training. You use these correcting forcings that you have computed during this time, and you use them afterwards. And it turns out that they work, and you get a good solution for much longer times than for the training. So this, for example, I think it's a very interesting idea, and we have already a couple of papers on that. So one's on computers and fluids, and it's on for one-dimensional Burgers equation. That was our proof of concept, let's say. And then we have now in archive the last one, which is on three-dimensional turbulence. So I think that's a very interesting thing because it allows you to, of course, when you go to the low solution with the correcting term, you can run a much larger time steps, right? So it's not only that you are reducing degrees of freedom, but you can run much faster this low order solution, right? Without losing a lot of accuracy. You lose a little bit of accuracy, but not a lot, right? So you run P8 and P3. Those are what you run. And when you're correcting, you're recovering P6, more or less.
That's so interesting. Could you walk us maybe through the training process? I think that would be very interesting for the audience. So you said you train the algorithm, your clustering algorithm, for example. What would be the input and what are the outputs of that model?
For the clustering? Okay. So
Yes.
for the clustering, what we use is the gradients of the velocity field. So some parts of the straight tensor and some different parts. Actually, this paper is also in archive if you want to check the details. And what we do is we only use two clusters. So the two clusters, so the way we are thinking of that is we want to get the viscous regions and the turbulent regions because those are the regions where we want to adapt the mesh. The rest, it's more or less potential flow, right? So you think of on an airfoil, far away from the boundary layer and the wake, you have potential flow. And potential flow, it's basically a region where nothing happens. So you can use P0, right? Whilst in the regions where you have the viscosity and turbulence, then there is where you want to have a high polynomial order, right? To capture all the flow features. So this is what we do. We use two clusterings, one outside these regions, one inside these regions. And with this, we have tried increasing the polynomial inside the region, and we get the same results as when we do an homogeneous polynomial order everywhere. So sure. That's a bit the idea with the clustering. Of course, we have tried a lot of different inputs, right? So you try some gradients, they don't work. You try other gradients, they don't work. And well, all this is reported in the papers.
Yeah, and I'll link it as well down in the description. Are there any other maybe applications that you use it for? Maybe we talk about flow control and sensitivity analysis. Is that also where you apply machine learning to it? And how can machine learning support these
Right.
fields?
We haven't used machine learning yet, or don't have any publications yet on that. But the idea is to use it in the future. What we do for flow control, or our approach to flow control, so far has been to use concepts from stability analysis and sensitivity analysis. So very briefly, what that means is you can run a solution and check and add a perturbation to that solution. So if you got an equilibrium solution, you add a perturbation, and you see if the perturbation will grow with time or will decay with time. So if it decays with time, you're a stable system, and if it grows with time, it's an unstable system. So this is stability analysis. What you can do with stability, when you couple that with a join method, which is basically a mathematical machinery to get some information, you can get the most sensitive regions to perturbation. So you can get regions in the flow or in the surface of your airfoil, for example, as well. We've done that, where if you make changes, you change, for example, the shape of the airfoil locally there, you will get a stable flow. So something that was oscillating then starts oscillating. So, for example, we have cases where we have done buffet. So buffet is when the shock starts oscillating because it interacts with the boundary layer, which separates, right? And eventually, at some particular condition, that starts oscillating. So this is something that it's bad for aircraft. So it's something to be avoided. And what you can do is where they interact, you can add some small shapes in the airfoil, and that will stabilize the oscillations. So it will stop oscillating. And so those are interesting approaches because you're not blindly trying to optimize things, adding any type of shape in the thing. You know the shape that you have to add from the mathematical analysis. So from these adjoins and from this stability analysis. And that tells you exactly the shape you need and what's going to give you the best the best damping, let's say, of these oscillations. So this is our approach. I think all these can be linked to reinforcement learning, for example, and this is something we're looking into. But we recently started, so we don't have publications yet on that. But I think there's a lot of promise on combining reinforcement learning as well with these type of approaches.
Very interesting. Yeah, I'm looking forward to it. If you have a publication, I follow you on Twitter, so if I see something, I'll definitely share with the community. I was wondering, how do you validate these solutions? For example, if you use machine learning for CFD, obviously you have to validate those, and I think it would be interesting to discuss how do you validate them.
So validation is always complex, right? So you always we try to work with experimentalists, right? So now one of my students, for example, is in 20, helping some with wind tunnels for aeroacoustics in this case. And we are trying to give them what we need, right? So we can then compare our CFDs to their experiments. So I think it's interesting to collaborate with experimentalists to know that we're comparing the same things and these things and get the insight as well, right? Because we're mainly CFD developers, but it's interesting to know how they do the experiments and what, how we can really match experiments and CFD. So that's what we do. You use experiments typically, or DNS, or very fine LES computations to validate the codes. But it's very difficult. We're also looking at uncertainty quantification to try to get some insights into how good are these validations, etc. But they're difficult questions. It's not easy to validate.
Before maybe we forget something on the machine learning and CFD part, is there anything you would like to mention before we jump, maybe closing the podcast and talk about the CFD resources that you would recommend? Anything about machine learning that we're missing?
Well, I think it's very interesting. It's a very exciting time, I think, to be a researcher, right? Because there's all these different methods coming up from other fields, which is not at all fluid dynamics. And we can benefit from those, and we can select the ones that can help us in the CFD world to accelerate or to get better results. So I think it's very exciting. I think it's interesting, and it's a good time for students to get on board and start PhDs or collaboration work on these topics, because I mean, I recently announced to the fourth year students if they wanted to do final degree projects on CFD and machine learning, combining these things, and I got too many requests. I couldn't take that many students. So I think it's interesting, and people know that it's interesting. Right? So it's nice. Well, I think it's going to be very nice during the next few years.
Absolutely. And we see the trend is going more towards like using machine learning for CFD with all the tens and hundreds of papers coming out every day or every week. How do you stay focused as a researcher and not get overwhelmed by the sheer amount of papers that come out
Very good question.
every day?
Very good question. I do get overwhelmed. So I think everybody gets overwhelmed. It does help a lot, the ResearchGate. I really like ResearchGate. It gives you, I don't know if you know this tool, but it gives you, the newspapers that are coming up. And I think that really helps a lot to get an overview of things. Of course, I'm not allowed, I cannot read all the papers that come in. So what I tend to do is send the papers to my students, the ones that are of the different topics. And they probably hate that, but I think it's kind of the way, it's the only way, right? And every so often you read particular papers or papers that are developing new methods that you want to apply a little bit in the future, right? Of course, when you write proposals, for example, to get funding, you have to read the papers. So you tend to force yourself to read papers, and that's the opportunity. And when you review papers, also those are opportunities to really carefully read the papers. But in the day-to-day basis, it's very difficult to keep track of different fields. So you do what you can, I guess.
Yeah, very good insight. You talked about funding, Spanish government and funding. I think they don't fit very well. What would you say to the government? Should they fund more projects like yours? What's your comment on that?
I think so. I think the percentage of investment in Spain for science in general is very low. It's lower than the average, I think, in Europe, which I don't think it's acceptable for a country that it's economically good. In terms of European standards, which is Spain, I think it's the fourth in Europe, something like that. So I don't know why this happened, but that's been happened for quite a few years already, and that there seemed to be a slight trend of changing that during these last 2 years, maybe, but that's obviously not enough, and that should be changed. I mean, it's very difficult. I mean, I was checking the other day on Twitter, and apparently Spain has it's pretty well positioned in terms of number of papers per year in worldwide, but with very little money. So when you look at the efficiency of the Spanish researchers, we are awesome, in fact, right?
Yeah.
But imagine what we could do with I'm not saying we need to be on top of financing, but at least in the average, right? Or at least above the average in Europe. So that's very frustrating. What tends to happen to us is that we don't apply. Well, we apply for Spanish funding, of course, which is not much, and then we apply for European funding, which is very difficult to get because there's a lot of competition. It's quite challenging, and we are quite successful in getting it. But that means that we spend a lot of hours writing proposals, improving proposals. And in Europe, the standards are you get so it's less of 10% success rate. Right? So that means that you write 10 proposals, you get one, if you're lucky, of course. So that means a lot of time spent in writing proposals. Where I guess if the Spanish system was better, then we wouldn't waste so much time. So the success rate would be 30% in Spain, for example. I think in the UK it was 34 last time I checked. Yeah.
Do you think there's any motivation behind it? Like, what would your hypothesis be why this happens? I mean, we could speculate now, like make speculations, but what do you think is the problem?
I think politicians, they don't see any good thing in science, and that's really bad. I think that might have changed a little bit with the pandemic, where people realized that actually having a strong research system or people that can develop vaccines and things like that, it's actually useful, right? But it's difficult to convince these politicians. So I'm hoping new generations of politicians are going to be a bit more science aware.
Yeah, a man can only dream. I was wondering maybe it has also something to do with politicians not having maybe a science background. They just lack the understanding of, hey, we need funding, and politicians simply don't get it.
For,
Maybe it's too far away from their expertise.
for sure. That also is it's a reason. I think you were a bit more lucky in Germany, right?
Yeah,
Yeah,
definitely.
but,
Definitely. Yeah, I hope, wish you all the best, Esteban, and I hope it will definitely become better for all the researchers in Spain, and maybe someone from the government who knows listens to this
hopefully.
podcast and say, okay, maybe we should change something here. To wrap this up, Esteban, any resources that you would recommend to students getting started with CFD, maybe intermediate CFD enthusiasts? What should they read? What should they learn from? Obviously, your videos that are coming out soon.
Yeah, I think. Well, there's some nice resources out there. I mean, you have some videos which are nice. There's a lot of CFD resources out there. There's a particular website of Jahid Hassan, a complete learning path for CFD, which gathers a lot of
Oh, yeah.
different websites. So that's a nice website because you get a lot of resources. Of course, it can be a bit overwhelming, but it's a good starting point. What I would recommend, however, is uh, do not neglect books. So don't forget about books. Books are a very nice way of learning. So it's not all about videos online. It's not about resources online and blogs. Those are very good. Those are very good. I'm not saying anything on the contrary, but books are very good as well. So remember to check nice books on the topic that you're interested in and reading the books thoroughly. So that those were written for very clever people as well, right? So they're interesting. Um, yeah, that's basically the advice. We tend these days to forget about books and go into Google, and links and stuff. And let's try not to forget books.
Yeah. What's your favorite book, Esteban, on CFD?
Of course, depends on the type of. The problem with books, of course, is that depends on the type of discretization skill. For example, there's a lot of books on finite volumes. There's a lot of books on finite difference. There's not that many books on higher order methods, for example. So I have preferred books for each category. So I like Ferziger's and Perique for finite volumes, for example.
Yeah.
I like Spencer Sheridan's and Karniadaki's book on higher order methods. That's very good. I like some the classic Wilcox of turbulence, for example. I mean, there's many, or Pope for turbulence. So depending on the topics, you have to select a book. Of course, each book is very thick, so you don't have to. You have to be patient, right, and read slowly.
Cool. Esteban, it was such a pleasure talking to you, and I hope maybe there will be a second part in the future. If you work on reinforcement learning for the applications we talked about, feel free to jump on another episode. I'm more than happy to talk to you about reinforcement learning for CFD, and maybe I can brush up my reinforcement learning skills in the meantime. It was really a pleasure, and I wish you an awesome rest of the week.
Thank you very much. Thank you very much. Have a good weekend, and I really like your podcast. So keep it going. Thank you.
Thanks a lot, Esteban.